Thanks very much. Good afternoon, nullcon. I hope you had a good lunch. Just to flesh out the background a little bit, I work for Google's Project Zero team. I have over 10 years of experience of researching on Windows, finding interesting logical privilege escalation vulnerabilities primarily. I suppose also, which is kind of important for this talk, is I'm one of the owners of the Chromium Windows Sandbox code. So I actually implement code in Chromium to improve the Windows Sandbox, and that's definitely an interest of mine. So follow me on Twitter or whatever, or pick up my book, whatever you want to do. So what is it I'm actually going to be talking about? So obviously, as I said, this is the flashback track. So in 2015, I came and talked about Windows sandboxing and the sort of difficulties around implementing them on Windows from a user mode perspective, and also sort of why they existed. So let's just recap a little bit of that sort of presentation just to get us onto the same footing. So of course, in the good old days or bad old days, depending on which side of the fence you were on, any application which was potentially processing untrusted content was probably just running as a normal user privilege, maybe even running as an administrator. And of course, if you found some sort of remote code execution vulnerability, well, then that's game over, basically. The attacker can come in, compromise your application, and potentially run code as you. Now, it seemed that the likelihood of eliminating remote code execution was pretty low. So instead, let's just make it more difficult for the attacker, once they get in, to actually compromise the rest of the operating system. And that's where sandboxes come in. Sandboxes add that extra hop from remote code execution to actually compromising the full system. And depending on how you implement them, depends on how good they are. So there are some sort of basic requirements for sandboxes, certainly for ones which you want to implement in a useful way. Now, first one is obviously you want something which is relatively easy to get into. You don't want to have to write specialist code which needs to take into account that it's sandbox. You kind of just want it to just work out of the box. But of course, you also want it so it's very difficult to get out of again. So if the attacker gets remote code execution inside your application, it doesn't mean they can then compromise the rest of the operating system. But we'd also want to protect users' data. There's no point like stopping you modifying the operating system if actually the attacker can just come along and hoover up all your private information, leak it off to a web server somewhere, and that's basically, certainly from a normal user's perspective, that's pretty much your crown jewels, right? So you don't want this to happen. You almost want the sandbox to also prevent you accidentally leaking your data. But of course, some older sandboxes weren't so good at this. The famous example is the Internet Explorer Protected Mode sandbox, which was pretty much the first major application which had sandbox, and certainly the first major browser which had a sandbox. But it did nothing to stop you having your files stolen from you. It would stop you compromising the operating system, but anybody running inside the sandbox could actually just read all your files and egress them out to anywhere on the internet. We also need to work within the limits of the operating system. I can't actually go in and modify Windows. Now, I could write a device driver which patched functions in memory and did something different, but I can't actually come in and change the actual physical code of Windows, ship that to all the different users across the world, because I'm not Microsoft. I don't work for Microsoft, and it's very difficult for me to do. So the sandbox has to be something which ideally we don't have to compromise the integrity of the operating system just to get a single sandbox. And kind of almost actually more important than the security is usability. If your sandbox is super, super, super secure, but it runs at like 10% of the speed of a normal application, well, no one is going to, in their right mind, want to sandbox their code, especially something like a web browser. It's just never going to happen. So it's got to be usable. It's got to be performant. If there is a performance impact, it has to be relatively minimal. So on Windows, unfortunately you can't see this, it's a bit blurry, but on Windows, most of the sandboxing you will see, application sandboxing, is done through utilizing the security mechanisms already built into Windows. And the main one is basically every single resource, whether it be a file, it be a process, have something called a security descriptor associated with it. And the security descriptor defines sort of the policy of who is allowed to access that resource and for what type of access, whether it be, say, read or write or execute. And the first step of having a sandbox is having, obviously, a configured list of these security descriptors. Now, for the most part, these are all sort of fixed for you by the operating system. Like the files in System32 already have a security descriptor, and you running in user mode shouldn't and couldn't realistically change them. But in that security descriptor, there's 3 pieces of information which are critical to enforcing security. That is the owner of the secured resource, something called the mandatory integrity label, and something called the discretionary access control list. And the DACL is basically the core of the security descriptor. It's basically the means by which you define what groups can access that resource. In terms of identity, you also have something called the access token. So each process has an access token, and this is the user identity, the user principal, and it contains the user's security identifier, which is usually seen in text form, but actually it's not stored by the kernel in text form. It's stored in this binary blob called a security identifier. And so all groups are actually these binary blobs really under the hood. So you have your user identity, you have your list of groups which you are associated with, you have a mandatory label or integrity level, which is sort of the counterpart to the security descriptor, and you have your privileges. And privileges is sort of a shortcutting mechanism. They almost like just single bit flags. Do I have this privilege or not? And so, for example, there's the time zone privilege, and the time zone privilege defines whether I can change the time zone. So rather than doing any sort of check or having to be in the time zone changer group, you actually have this privilege. So when you actually try and access a resource, you define what access rights you want. So I want read and write access to this file, for example. Something simple. And the kernel will then go through this access check operation, which consists of 3 major steps. The first one is a checking of that integrity level. Now, basically, the integrity level is just a number, and like in a really simplistic terms, if your token's number is less than the resource's number, then you cannot write to that resource. You can only read from that resource. That is a gross oversimplification, but it suits us for now. You then have something called an owner check, and the owner check just is there to prevent you locking yourself out of your own files. We don't need to worry about that too much. But really, the DACL check is where it's all at. The DACL check is where we check that list of groups in the security descriptor against our list of groups and our access token and determine whether you've got full access or not. And the end result is either you're granted access for whatever you desired in the first place, say read write, or you get denied. You can't request read and write, and then the check only goes, oh, well, you've only got read, so I'll just give you that. It will just deny you access. If you ask for more rights than you've got, it will deny you. Now, when it comes to sandboxing, this access check changes subtly. We add 2 more boxes, and what actually happens under the hood is sandboxes use special types of access tokens. Now, for Chrome, we tend to use restricted tokens or filtered tokens, depending on what side you're seeing them from. For things like Edge or Universal Windows applications, they use something called app container tokens. But fundamentally, they're doing pretty much the same operation. And what actually these access tokens allow you to do is specify a secondary list of groups which are only used for this sandboxing access check. So when you do the DACL check, it will obviously first run through your standard group list and go, okay, you've got read-write because you're Alice, and Alice is granted read-write on this file. However, it will then go, okay, now I'm going to check the sandbox SID list against the same security descriptor. And of course, the sandbox SID list should have arguably different groups than what is in your standard group list. And if those two checks don't match, so if your normal check says, yes, you got read write, but the second check just says, no, you've only got read, then you go to deny access because it goes, well, you can't actually get read write because your secondary check failed. And that's basically how sandboxes work on Windows at a very, very high level. So this is the sort of typical architecture you'll see. You'll typically have some sort of privileged broker process. When I say privileged, all I mean is it's more privileged than your sandbox process. So Chrome, for example, runs its broker at a normal user privilege. However, Edge runs its broker inside an app container, and it just uses some funky tricks to then sandbox processes further on from that, as we'll see later. But the idea here is that sandbox process only has a restricted set of accesses to normal resources. It may only have read access to a set of resources, for example. But of course, at some point, that sandbox process may go, hey, I really need to write to this file. At which point it has to go to the broker, and the broker takes the request and says, okay, you want to access this file for write access. I'm going to check it against some sort of internal policy or some mechanism to determine whether that's okay. And I will open the file for you and then pass you back access to that resource. And pretty much all the sort of common sandboxing models use something very, very similar. Of course, the devil's in the details, and it gets obviously considerably more complicated as we go along, but fundamentally that's basically how it works. So I continued my previous presentation with discussions of things like attack surface, how difficult it was to reduce attack surface on Windows, especially from the system core level and from the device driver level. And there obviously was some ways you can mitigate some of this, but it is kind of difficult things to achieve. I also talked about how you couldn't lock your process down too far, because if you change your access token so that it had access to nothing, then it would actually crash the process when it started up. It wouldn't even be able to load a DLL, so that when it tries to start up, it failed to load DLLs. And then I was also talking about ways of abusing the operating system functionality to benefit exploitation. So you find bugs, so you have a resource planting bug, and in this particular example I showed I could use a symbolic link inside the registry and utilize that resource planting bug to escape the sandbox. So that is basically my quick run through of the previous presentation. So let's welcome in 2019. It is 2019, right? Yeah. Whew, thank God for that. What has changed in the past 4 years? Well, what has changed from a Microsoft perspective is Windows 10. Windows 10 was released towards the end of 2015, so pretty much just after my presentation. And for various different reasons, this has had a fairly significant impact on the security of Windows in general, and also on sandboxing in particular. Now, the first one is Windows 10 was the first version of Windows to basically make updating pretty much mandatory. You have no choice anymore. You can see examples of videos of people playing some cool online game, just about to shoot someone in the head, and then the machine reboots and says, sorry, I'm updating Windows. And this is the thing, in Windows 7, Windows 8, you can just turn the Windows Update service off. There's nothing stopping you. You won't get any more updates, but hey, I don't care. But of course, there's no point writing the most awesome sandbox in the world if you're leaving effectively public, sometimes trivial privilege escalations which you can abuse to escape the sandbox. So enforcing updates is generally good for security, if not necessarily for your online gaming profile. The other interesting thing is the time to release. Now, unfortunately, the text is a little bit small on the screen, but basically this is a sort of really simple graph of the number of days between each major version of Windows, starting at NT 3.1 and going up to Windows 10 1809, which is the current released version. And typically, Windows release cycles were, we release to RTM, and at some point in the future, we may have a service pack and then another service pack and so on. But service packs didn't typically include substantial changes to the operating system. And of course, they were multiple years away, potentially. But you can kind of see it kind of is, I don't know, averaging a couple of years per major release up until Windows 10 where it crashes. And then all of a sudden, Windows 10 is basically driving towards a 6-month release cycle. And it's not just that Microsoft are releasing quicker. They're adding much more functionality into these releases than ever before, like major structural and security changes in each major release, which means that it's a much faster turnover of new security features in theory, because instead of waiting 2 years, 6 months down the line, you could guarantee that, say, 25% of the install base of Windows 10 will now have this new funky feature which allows you to do sandboxing better. And a lot of that comes from Edge. So Edge obviously has its own sandboxing requirements, and there is a symbiote. Oh, well. There's a symbiotic relationship between Microsoft Edge and Windows. Obviously, they're both written by Microsoft. And so if Edge says, hey, wouldn't it be cool if we could do X? Then the Windows operating system team could potentially do X. And I don't know whether it's my... Wonderful. Okay. Don't know whether it's my cable. That's never a good sign. Well, the slides in some ways are not that important, to be fair. Let's just carry on a little bit. So you've obviously got Edge, and Edge is, well, that's actually a much better picture. One of the things with Edge is that it utilizes the existing app container sandboxing feature which Microsoft added into Windows. And this was added originally for store applications. Oh, God's sake, bloody Windows. Why do I use it? It's like, I'm turning off distractions because you're doing a presentation. Well, stop popping up bloody dialogue saying... Anyway, I digress. So, app containers was an attempt by Microsoft to actually implement a more fully featured sandboxing primitive. There used to be the old restricted tokens which Chrome still uses, but app container was kind of reimagined and getting rid of the legacy stuff and building something new. And one of the ways in which this had a major advantage is they could change the operating system behavior because there was no real backwards compatibility issues. And one of the things they actually changed was relating to device drivers. So device drivers, if you have to opt in for them to be properly secure, which seems kind of odd. But if you look at it through the prism of a device driver on Windows, it's actually a file system driver. The file system component is actually just maintained, the security of that is maintained by the file system driver itself. So if you don't opt into security, the operating system thinks you're just a file system driver and you're going to deal with the security, right? What Microsoft added was actually now, in order for a device driver to act as if it's a real file system driver from an app container, you need to specify a special flag when creating your device. Otherwise, it just won't even allow you to open it. And this flag seems to even be kind of hidden away. It's not documented on MSDN. It's just sort of there. And I guess the idea is that hopefully no one uses it, and therefore you won't have any attack surface problems. And so this does massively reduce attack surface issues. Another thing in app containers, in Windows 8, you had these capability SIDs, and these capability SIDs are those sandbox SIDs, which I talked about in the access check. And Windows 8 just had like a fixed set of capabilities. You could kind of define your own, but the trouble with sandbox SIDs is they must be in a security descriptor somewhere for them to be enforced. If they're not in a security descriptor, they're never going to get used. So the fixed set of capabilities were quite limiting in that regard. What Microsoft added in Windows 10 is basically you can now create sort of arbitrary capabilities. They still have to be put into some sort of security check somewhere, but they're much more flexible so that you can just add a load of new extra cool ones. And actually rather than actually having to manually define like incrementing numbers, they're just generated from a SHA-256 hash of the name of the capability. Unfortunately, there's no provision to directly reverse this value back to a string. So you have to kind of have a big list of strings which you know are capabilities, and work out the SIDs, and then that allows you to convert them back. So in my previous screenshot, these names are all generated because I know that these capabilities exist, and I have to kind of match them up at runtime. Now, a secondary issue was, in app containers, you had multiple packages. So the idea is, say, Calculator is a different package from Edge, is a different package from Cortana. And of course, you don't want the calculator being compromised and then using that to compromise Edge or something equally crazy, right? But of course, you also want resources which are accessible by everybody. So Windows defined a special SID, this all application packages SID, which was kind of like a hard-coded, no matter which package you're in, whether you're in the calculator package or the Edge package, you can access this resource. And that's perfectly fine, like it makes sense. The trouble was, now that you had this facility, you ended up with security creep. You basically ended up with everyone going, hey, we need our application to be accessible from an app container. We're not really sure which app container just yet. You know what? We'll just stick all application packages and worry about it later. And then, of course, no one comes back to worry about it later. So loads of comm services, for example, were exposed to Edge, but had potentially like privilege escalation vulnerabilities, but there was nothing really you could do about it, because if you remove this access from the security descriptor, then every other app container would suddenly start failing. So what Microsoft did primarily for Edge is introduce something called the low privilege app container. And what this does is it makes that matching of all application packages basically a opt-out. So Edge can opt out to this all application packages SID, and it then has to rely on capabilities. There is also the all restricted application packages SID, which hopefully won't get the same security creep, because basically this is really only Edge using it. So hopefully, again, no one will care. No, of course, Edge is going away, but it was nice while it lasted, right? And the final trick that was added to app containers for Edge is child app containers. So previously you created a package, you had the calculator package, and calculator could spawn subprocesses, but those subprocesses run with the same effective identity as the parent, as you'd expect. Of course, for something like Edge, you've got a problem. Like, what if I want to segregate internet content from intranet content? Well, they're all in the same package. I could create multiple packages, I suppose, but that doesn't seem very effective. So Microsoft added child app containers. So a single app container can create its own children, and those children then have different security principles, and therefore you can enforce, like, the parent can write to the child, but the child can't write back, and things like that. So this all featured together to make Edge certainly more secure. And in theory, these can be utilized by other sandboxing applications. So that was sort of like on the app container side. So sort of almost differences in how access tokens work and the security check works. Let's now talk about mitigation work. So another strand of Microsoft security development cycle is basically to try and remove, like, make it more difficult to exploit vulnerabilities, both from a we don't want people to get RCE too easily, but also from a, we don't want people to be able to escape the sandbox too easily. And how can we do that? So I mentioned right at the start, like registry key symbolic links, and this I found like an incredibly useful technique of using symbolic links on Windows to basically exploit resource planting attacks. Now, there's various different types of symbolic links in Windows over the years, but the thing which has changed for Windows 10 is they've pretty much been banned. So all these cool techniques I've built up over the years to exploit these types of vulnerabilities have now been banned because Windows 10 has banned them. And this actually has also been backported to, I think they backported it to Vista, a lot of these changes. And then this all revolves around this RTL is sandbox token function. And basically, this function just returns true if you're in a sandbox. And that's pretty much everything from Edge protected mode to Chrome to Edge, IE protected mode to Edge to Chrome. They're all considered to be sandbox processes. So, registry key symbolic links. If you're in a sandbox, you can go away. Access denied automatically. Well, if you're in a certain type of sandbox, no. Banned. But for something like mount points, which are like directory symbolic links, unfortunately, Microsoft found out that Silverlight, for example, used these, and Silverlight was being sandboxed, and so you are kind of now in a situation where compatibility reasons stop you from blocking this. So instead for mount points, what they do is you can create them, but only if the target directory is writable by the sandbox user. And in theory, that should prevent you from exploiting these. Unless you can find a bypass, of course. So I found like 2 or 3 bypasses, and of course Microsoft went, okay, we'll fix these. So like they fix the exploit, but not the root cause. Okay, fair enough. After a few goes at this, eventually this mount point mitigation got written in such a way that it was actually pretty robust. So I just found different things to abuse instead. So, hard links. NTFS supports hard links. Maybe I can abuse hard links instead. So of course, Microsoft goes and fixes that as well. And if you basically like bring up the kernel in IDA on a modern version of Windows 10, do like a cross-reference for RTL is sandbox token, you'll find various callers to this, and you can actually trace through them and see what they're doing. It's also an exported function, so device drivers could call it. So a recent one is the common log file system has introduced this, which is like been abused a number of times as well. And this can now call that and go, okay, I'm in a sandbox, so I'm just going to deny you access to that resource. Now, those I would say are sort of implicit mitigations. They're things which just are enabled by default of you being in a sandbox. But Windows also has explicit mitigations which you need to opt into. And you usually use like set process mitigation, policy function, or various other techniques. And there's actually quite a few. And obviously, as you can see on the right, these are supported in Windows 10. The number of mitigations has been expanded. And I think there's actually some which sort of fell off the bottom of the page somewhere. A lot of these are focused on remote code execution, but some of them are not. So, like, for example, attack surface. So we had this problem that the kernel itself has like 400 system calls, and these are obviously major attack surface because if you find a bug in a system call, well, you've probably got kernel code execution. But of course, there's also Win32k, and Win32k is a mire. It's absolutely terrible. Like, Microsoft have done their best to improve it, but it's still problematic. I think like there was even a very recent 0-day which utilized the Win32k bug. So we want to get rid of that, and Chrome does get rid of that. There is, in Windows 8, they introduced the Win32k system call disable mitigation policy, which completely eliminates access to Win32k. The trouble is, Chrome spent like 2 years of engineering effort to implement that. And it basically required you to remove every single explicit and implicit call to GDI and user32, which is pretty much impossible to do. And it kind of goes against the idea at the start of having a sandbox, which is easy to get into. It's easy to write code, which ends up being sandboxed. And of course, if you happen to avoid Win32k and writing Windows code, it's pretty much impossible. And of course, Microsoft saw this with Edge. They couldn't easily remove every single call to Win32K because it's too mammoth a task. So Microsoft introduced the Win32K system call filter inside Windows 10. And instead of a hard block of everything, instead, you have a filter profile which says, okay, these 50 calls in Win32K are okay to call, or these are at least the calls which we know you use. The trouble with this from a generic sandboxing perspective is it's impossible to change this list of filtered functions. I think the current implementation has 3 or 4 filter profiles, so you could have different sets of these, but they're all designed for Microsoft products. So they're designed for Edge or Edge with Flash running or various other components. And so they're not actually that useful from a user perspective, but maybe one day they'll expand this to be more generic. What is probably more directly interesting is the ability to block fonts. So if you follow my colleague Mateusz's blog posts and work a couple of years back, he was basically just using true type font bugs to basically break into the Windows kernel. And fonts are a terrible thing to be passing in user mode, and Windows parses it in kernel mode because why not, right? True type fonts have sort of a little VM which runs code to generate the hinting and stuff, crazy stuff like that. It's absolute nightmare, right? But the main danger from this is fonts which aren't provided by the system. If you have a system font which is installed in a secure location and it has a privilege escalation in it, you've probably got bigger concerns. So what Microsoft decided to do is let's have a policy which basically blocks non-system fonts. That being either fonts loaded from a memory buffer or fonts loaded from a non-system location such as Windows/fonts. And this works pretty well. The trouble is, even web browsers, they like to use web fonts, for example. And if a web browser wants to render this using GDI, well, it can't because this mitigation's in place. So it turns out actually at the same time, some other team, well, ignoring the fact that of course you can bypass this mitigation because of course you can, right? Someone else in the Microsoft team was also working on something called the user mode font driver. And the idea here was if you try and load a non-system font, instead of parsing it in kernel mode, we're actually going to parse it inside a sandboxed process running as a normal user. So yes, you could find some exploitable vulnerability in a particular font. However, all that would really give you is the ability to compromise another app container process or another sandbox process. And so you've not really gained too much. Well, except for when there's bugs, right? But let's just ignore more bugs in these sort of features. And this is kind of the double-edged sword of this rapid Windows 10 release cycle. In that, on the one hand, yes, you can ship new security features really quickly. You can also ship all manner of other crap at the same time, which has security vulnerabilities in it. And so the number of times I found bugs which are basically new functionality added just to Windows 10, it's pretty high because I'll just go, okay, what have Microsoft added in this latest version of Windows 10? That looks interesting. Maybe I should go and poke at that. And more often than not, you'll find something interesting. Even if it's not a full vulnerability, you'll find some new cool feature. For example, those symbolic link mitigations, Microsoft added in 1709, I think it was, which is 2 versions back, a new symbolic link type, which was hey, this is a global symbolic link. It's used for their container support, their Docker support, but technically utterly useless for anything but something running Docker, which is no consumer version of Windows whatsoever. But because someone had just added it as a backdoor kind of thing, all of a sudden it allows you to bypass the symbolic link mitigations. Well, that's kind of unfortunate, right? But it's all new, this new code, which, has anyone actually used containers on Windows? Wow, one person. That's amazing. I'm surprised they even had one. So it's a really niche feature, and yet you're compromising the security of your operating system for this very niche feature, which shouldn't probably even ship in Windows 10 Pro, right? Or maybe certainly not in Windows 10 Home. Anyway, I digress. So the interesting thing about some of these mitigations is that there's no consistency of whether they get inherited across process boundaries. So really, like, for example, like disabling the fonts. If you can create a new process from your compromise process, well, then that process can now talk and create custom fonts, and therefore you can use that process to compromise the kernel. So all we need to do is spawn a new process. And of course, for most Sandbox processes, that's pretty easy, right? You can just spawn a copy of Notepad, inject yourself into Notepad, and then compromise away. So, for example, Chrome uses something called a job object. And a job object has been around since like Windows 2000, and it has a process quota which says how many processes can be within that job object, and you need special privileges in theory to escape that job object, to break away from it. So what happens is you create a new process, but it gets charged against your job object, and it goes, well, you've created a process, but now you want two processes in your job object, but you don't have quota for two. You only have quota for one. So it kills the process and it dies. And this works fine, except for where you find a route which allows you to spawn a process outside of your job object. So WMI, for example, I'm sure many people in here have probably used the Win32 process create function. That runs outside of your job object, intentionally so. And so if you can get access to that from your sandbox, you can spawn a new process. So what Microsoft did was, to try and mitigate this somewhat, is they introduced a new mitigation, which is basically disable child creation. But rather than doing it on a per process basis, which is kind of all the job object was doing, they added it to your access token. And the reason this is interesting is that obviously when you spawn a process directly, when it just clones your current access token. But when you spawn it via WMI impersonates your access token. It basically takes a copy of you and impersonates you and pretends to be you. And that flag gets copied across. So when WMI tries to create that new process, well, it can't do so either. And so by doing this mitigation, you can block both direct instantiation routes and indirect instantiation routes. Well, except if you find bugs in it, right? But anyway. So the final sort of interesting change, certainly from my previous presentation, is I gave a little bit about like a bug I found in Chrome, which was related to sharing of resources. So when you create a resource, you can optionally provide it with, some of them allow you to optionally provide a name. And section objects, for example, which do memory mapped files, you can provide it with a name of that object. And if you do that, then it gets a security descriptor. And so what Chrome was doing was, in its main process, it was creating a writable section and then copying it to the Sandbox process and saying, but you're only having the rights which allow you to map it as read-only. And relying on this behavior to prevent that Sandbox process converting it back to writable and modifying the section data, which could cause security implications. However, Chrome didn't have a name. And due to a quirk in the Windows kernel, that also meant it had no security descriptor. And what that allowed the Sandbox process to do is it could just reduplicate the handle, convert it back to a writable handle, and then map that memory writable and just modify it. And like I used this to modify a Grease Monkey script, which then got loaded into pretty much every renderer, and you could just execute code on that page, including web UI pages and stuff like that. Now it turns out, actually in Windows 8, I even missed this in my previous presentation. In Windows 8, Microsoft did finally add the ability to assign a security descriptor to an unnamed resource, such as a section. So you can actually now apply this security descriptor, and it will now get enforced by the Sandbox. But of course, if you find someone who's duplicating section handles and relying on the permissions to restrict what that process can do, then potentially you've got a security bug, not just in sandboxing terms, but in general. So I think I'll see if I can do just a very quick little demo, but we probably haven't got quite as much time, unfortunately, as I was expecting.
5 minutes.
Yeah, 5 minutes ago. So I spend a lot of time trying to write tooling to improve my ability to inspect sandboxing, especially attack surface stuff. Unfortunately, the resolution's not too great, but you've got a tool, for example, to inspect access tokens. So you can see, for example, this is our group list, and you can go through all the different components in here and just inspect it in a nice GUI form. But of course, you can also say get, if I get a file, system32 folder, and access read control. Then we do also have a GUI for, say, looking at the security descriptor. And so this is the security descriptor. There is, of course, existing Windows UI to view security descriptors, but they're actually usually hiding information. They hide certain types of access information and things like that, which you really want to see if you want to inspect it from a security perspective. And then you can basically just do, you can actually perform the security check yourself, as long as you've got if you've got a security descriptor and you have an access token, you can perform that check and actually analyze what access would be granted from any particular application. So, for example, if you took the access token from an edge process, you can utilize that to do a security check. So, if I just get process, so Microsoft Edge. Okay, so it's that ID. So we do entity token, process ID, that one. So this is our Edge access token, which also has this app container tab, which is all your capability SIDs. And if I, for example, do get entity granted access, I can pass it the directory, the system32 directory, and I can pass it the token from Edge, and it tells me, unsurprisingly, that Edge can access this for read, control, and all that sort of stuff, all the different types. But if I pick a different thing, so I pick, for example, my current process, access, read, control, and pass that instead, in theory, I should have 0 access to that resource. And then finally, of course, if I do it to myself, obviously I can open my own process for all access, and so that's all good. Anyway, very short, I'm afraid. Just a couple more slides, just to go over a few extra things. Hyper-V, Microsoft's hypervisor, is now coming to be everywhere. And this, of course, if you can stick stuff in a virtualized environment, then you can obviously make things more secure in theory, because virtualized environments are a much stronger security boundary in general than it is like a standard user mode sandbox. The price you pay for virtualization obviously comes down to performance. Like, you've got memory impact, you've got general performance impact to doing this. So yes, it's kind of a cool idea, but at the moment the performance just really isn't quite there yet. But maybe soon. And the other thing I had in my previous presentation was something called Pico processes. And Pico processes allowed you to redirect system calls. And it now exists in Windows 10. It's cool. Except the only thing you can do with it is run Linux, which is cool as well, but perhaps not quite as cool as a really awesome sandbox. But anyway, that's it's still pretty cool. So, in conclusion, so Windows 10, I think, actually has had some of the biggest impact on sandboxing in a while, even compared to Windows 8, which took things a sort of another step. But a lot of that came from not only the symbiotic relationship between Edge and Windows itself, but of course that faster release cycle where those new mitigations could be shipped like on a very, very regular rate. And there's so much stuff I would still like to see. Better syscall filtering, for example. Like Linux has setcomp. Windows really either has turn off Win32k or nothing. And there's very little in between. And like, there's things like that bootstrapping problem I mentioned very, very early in the presentation. Still a problem today. And unfortunately, it doesn't look like it's going away anytime soon. So I think we probably don't have time for questions, unfortunately, but thank you for listening. And if you want to ask me questions, I will be around for the next couple of days. You can bug me there. So thank you very much.
Thank you, James.